We started section 3.2, addition of whole numbers last time, and we looked at some models, two different models, one being good for objects that are actually sets where we don't worry about how big or how small or whatever, right? I count the blueberries, I don't worry about how big the blueberries are. And then models for addition that are number lines where the size matters, right? Like how many ounces of blueberries do I have? We're working with whole numbers no matter what we're working with because that's what this chapter is about. But there are some things that we measure and they actually could be measured in fractional values and things that we really wouldn't. So those are the two different models. And we also talked about our properties of whole numbers. There were four basic properties. Closure, the idea that whole numbers plus a whole number equals a whole number. Commutative, the order of addition doesn't matter. Associative, the grouping of our addition pieces don't matter. And then the additive inverse property as well. So we're going to look at some basic addition strategies and then algorithms today. So some basic addition strategies. Some of these are probably very familiar to you. There we go. And some of them may be less familiar. So counting on is a very common basic addition strategy. So if you had two numbers, you would start with usually the larger number, and then you would simply count up until you add that many more to the lower or to the other value. So for example, if you had, we'll just use some small numbers to start with. So something like 5 plus 2. You'd start with 5 and then you'd go 6, 7, right? And you'd add 2 more on your hand or whatever. And you'd say, I ended up at 7 by counting up from my 5. Doubles is a relatively new strategy in the sense that it hasn't always been around as a common strategy. Certainly was not when I was doing mathematics at this age level. But my kids have seen it from my 14-year-old at least down. And I can't tell you what happened in between the time that, I was there and she was there. But I know that it's been around at least since she was there. So this is the idea that kids actually learn the doubles first. So they learn what 1 plus 1, 2 plus 2, 3 plus 3, 4 plus 4. Those are the ones that they start with learning. And then when they want the numbers that are nearby that, for example, 3 plus 4, they know what 3 plus 3 is and then just add one more on. Okay? It's one more than a double 3. So that's a double strategy. Another strategy that is a common strategy is the idea of making tens. So recognizing that there are certain values that add together to be 10 very nicely, right? So 2 plus 8 and 3 plus 7 and 4 plus 6 and 5 plus 5. And so knowing those values that add together to make 10. So when you see values that don't quite add together to make 10, you can work from there. So 8 plus 6, well, 8 plus 6 is not very friendly, but 8 plus 2 would be great. If I had 8 plus 2, I know I would have 10. And so the 2 and the 6 are 4 apart. That's what you see adding the 4 here at the end. So then I would add 4 more on to my 10. So some of you may be struggling with this and you might be thinking, shouldn't they just memorize all their basic facts? And I would tend to agree with you on that for the most part. But what I think that you need to remember is that there are some kids for whom memorization is a really big struggle. Either because they have a learning disability causing that, or maybe just that's how their mind does, it's just how their mind works. It's not a learning disability, it's just not a strong suit for them. One of my children struggles with memorization quite a bit. I don't think it's a learning disability kind of struggle, but it's harder for that child in my home than for the others to memorize things. She has to work harder at it. So for her, having sort of strategies, hers is a multiplication issue more than the addition issue, but having strategies where she can come up with the answer quickly, right? Not quite as quickly as if it were memorized, but quickly is a really big beneficial thing for her. I also worked in a classroom once of one of my children, and there was another child in the classroom that truly had a learning disability. And so having strategies in that particular child's case for multiplication, again, I know this isn't an addition issue, but the same thing applies. Having strategies for that child to be able to get the same answer without having the fact that she's got a learning disability for memorization was a really big thing for her in her classroom. So keep that in mind as you're looking at these strategies maybe and kind of feeling like, why don't they just memorize them, right? Is that it doesn't work that way for everybody. And so we have to sort of make accommodations sometimes in ways that maybe we're not inclined to think are normal or necessary. I want to show you some algorithms for addition. So we're going to be looking further along at, some of these are going to feel much like ones we've already seen. But they're going to get numbers that are maybe larger in different cases, okay? So the first one is called a concrete model, and the concrete model looks a lot like our base 10 blocks, okay? So the base 10 blocks that we were looking at back in section 3.1, where we were doing things with base 5 and base 3, and I was saying, well, or base 4 and base 3, base 4 and base 5, whatever it was. And we were putting them together and we were saying, well, let's just combine them together and then we can make a long, or let's just combine some longs together and we can make a flat. That's what this strategy is, but in base 10. So the concrete model says if I have the number 34, what it could do instead is I could actually consider that as 3 longs. My longs are not perfect, so yours don't need to be either. And 4 units. Okay, so this is concretely taking 34. And then concretely taking the 1 long and the 8 units. And if you wish in your classroom, what would even be better than my drawing a picture, of course, is actually having kids take the concrete blocks, right? Like physical, hands-on, kinesthetic learning, right? Where they take the blocks, and maybe they're even Legos. That'd be amazing if you brought Legos in. I mean, within reason, you might not be able to get the Legos back because they just might be consumed and not focusing on math anymore. But it might work, right? It depends on your class. And they were actually able to take 3 longs that you had created out of 10, Legos, and the 4 individual Legos, and 1 long and 8 individual Legos. And what they're wanting to do is combine them together to get as many longs as possible. And all longs have to have 10, Legos in them or whatever. And so you actually take them and you say, okay, look, if I take these 8 and 2 more, what happens? I've created a long, right? So how many longs do I end up having? Well, if I combine them all together, how many longs do I end up having? 5. I have the 4 that I already had plus 1 more that I've created. So I have 1, 2, 3, 4, 5 longs. And how many units do I have? 2 units left over. So what number does this diagram represent? It's 52. And if you start here, you can extend this idea to talk about what happens in the standard algorithm, the one that you've learned and know probably better than anything else that I'm going to show you. And you can talk about the fact that when you do this with the standard algorithm, 34 plus 18, that's exactly what you do, is you look at the units. Hey, there's 8 and there's 4. And when I add the 8 and the 4 together, just like in my picture, and count them up, I have 12, right? But 12 makes 110, so I carry the 110 over the, not 110, but the 1 long, that's a 10, over to the tens column, and I have 2 left over to write underneath, right? That's what I'm really doing. I'm really doing something called regrouping. And regrouping is sort of the new catchword that you see in all the curriculums all over the place. Nobody calls it carrying anymore. Did you know that? I still do it when my kids are talking to me and they kind of look at me like I'm speaking a weird language or something. But they call it regrouping, okay? So they've regrouped. They've taken what was once the number 12 and they've regrouped it into 110 in the tens column and 2 1s in the ones column. And then they add the 1, the 3, and the 1 together to get the 5, okay? It's from regrouping. Kind of an in-between step in between the concrete model and the standard algorithm is the expanded algorithm. And we've done expanded algorithm stuff. It's still on my board right here by writing things with their place value next to them. And this is a version like that. So instead of thinking about the number 34 as 34, you think about it as 30 and 4. Or if you really wanted to, you could write out 3 times 10 plus 4. That's another version you see of it. Okay, both of these are expanded algorithms. And then the number 18, you don't think of it as 18, you think of it as 110 and 8 1s. Or you can write it as 110 like this and 8 1s like that. Okay, I'm kind of a fan of this one right here that I'm writing first because I think it breaks it apart very nicely by place value without making it look overly complicated or overly burdensome. And it does things very nicely. The nice thing once you've broken it apart like this is you can add from left to right if you would like to. You can do that. So I could actually say that this is 40 plus 12. Now, I'm not finished with my answer, right? I'm not. But I can write it that way, and then I can break apart the 12 again into 10 and 2. And then these two can be combined to give me 50. I'm writing a whole bunch of steps that you don't have to write all of them down. But this is how you would explain it, right? You're breaking things apart by place value. And that's called the expanded algorithm. Each one of our algorithms kind of have sort of, people they appeal to and people maybe who they don't appeal to. So you might look at this and say, man, that was a whole lot of steps. And it is. It is a whole lot of steps. And would we like the students to eventually use the standard algorithm because it's quicker? Well, of course we would. But if it takes a few times of doing something like this to get to the point where they're doing this standard algorithm successfully, it's probably worth their time. Another algorithm that's interesting, actually this is a typo, I didn't get this fixed from my previous slides. It used to be called the left to right algorithm. What's it called in your notes right now? Yeah, they call it column addition. They changed the name. Whether you call it column addition or whether you call it the left to right algorithm, it does the same thing. The idea is that it's separating each of our values. Here's 15, 34, and 32, 18. And you're adding them by column or by place value from the left to the right. So you're saying, hey, I've got a 1 and a 3 here. That's really 1,000 plus 3,000. And if I were to add those together, I would get 4,000. And so I write the 4 in the leftmost column and I put zeros everywhere else. And then you go to the next column, right? So you do the 5 and the 2. It's not really 5 and 2. It's really 500 and 200 that I'm adding. And when I do that, I get the 7 in the 5, 2 column and zeros in the other columns. So that's the number 700. And I move to the next column. I have 3 and 1. It's not really 3 and 1. It's really 30 and 10, which is a 4 in that column, or the number 40. And in the last column, the 4 and the 8, well, 4 plus 8 is 12. But that's a 2-digit number. That's okay. Any 2-digit number would end in the ones column here. And the 1 would simply be in the next column over, which lines up nicely. And we can add the values that remain. And most of things are not added to anything, right? It's a lot of zeros going on here. So the lovely thing is that you can really still add from left to right. This is 4,700. There's a 4 plus a 1. That's a 5. 52. Again, maybe we don't want to do this forever, but if it gives concrete understanding to the fact that the values have place value quantities to them and don't just mean 3, they really mean 3,000, there's some value to that. The lattice algorithm is the next one. This one's a cute one. It does a really good job of isolating the values that what we would call carry over. So I have 1,894. 3,218, just the same numbers as I had before. And I'll write a box underneath them. The box will be split into however many place values I have. So this one has 4 place values, so my box is split into fourths. And then what we're going to do is we're going to actually split each of our boxes along a diagonal like this. That's what makes it called a lattice. So what it does is it gives sort of 2 different areas within the box for the addition that you're going to do. So it really doesn't matter if you move from left to right or right to left. So when I add, we'll just go from left to right because we read from left to right. So 1 plus 3 is 4, and so the 4 goes in the bottom corner of the box. But then when I get to 8 plus 2 and I get 10, I put the 1 in the top corner and the 0 in the bottom corner. That's how I do a 2-digit number. So anytime you add two units or two single digits together, you either get 1-digit or 2-digit answers. So I've got 9 plus 1, that's a 1, 0. And I've got 4 plus 8, which is a 1, 2, or a 12. So what it does is it isolates the individual addition of the columns, right? And then what we do is we add them together along diagonals. So these diagonals that I made actually represent the place values that occurred. You do have to start in the bottom right-hand corner for this to work. So there's a 2 over here, a 1 here, 1 here, and then 4 plus 1 is 5. The reason you have to start in the bottom corner didn't show up on this problem, but if you did end up adding anything along the diagonals that added to more than 10, which it could, you'd have to carry it to the next diagonal over. So that's why you do have to move from right to left at that point instead of doing it whichever direction you wish. Any questions on that one? Okay. Opposite change algorithm. This is actually one that the book added in on this edition. And I'm glad that it did because it's a really good example of addition. It goes very nicely with one of the subtraction algorithms that they've had in the book for quite some time. So go ahead and write it out just like we have the others, 48, 231. The opposite change algorithm works very nicely it's attempting to avoid regrouping, avoid carrying things over. That's what it's really attempting to do. And it's also attempting to make the numbers nicer to work with. In other words, man, 488 is really close to 500, and 500 is so much easier to add to things than 488. Are you with me? So it would be so much nicer if that number didn't say 488, but it instead said 500. So what do I have to do to make that happen? Well, it'd be really nice if I was able to make that happen by adding a little bit to something. So the first thing that you might think to add is the number 2. I mean, I can get from 488 to 490 pretty quickly, and it's much nicer than it was when I had 48. But I can take 490 and I can get to 500 by adding the number 10, right? And I'm at 500. Now, I'm not rounding. It's not what I'm doing. I have to compensate for these adds that I did, these additional pieces that I add on. I got to compensate for that. And I compensate for that by doing the opposite of the value to the other number. So if I added 2 to 488, I got to subtract 2 from the 231. So what's 231 minus 2? 229. And if I added 10 to the 490, I have to subtract 10 from the other number, the 229, and I would get 219. But the beautiful thing at the end is that the addition ends up having lots of zeros in it, which is really the goal. So when I add the numbers here, I have 719, not a lot to add because most of them were zeros to begin with. Okay, does that make sense? All right. The scratch algorithm is particularly useful when you're adding a list of numbers together. This is one of my favorites. Takes a little getting used to, but it's very cool. So here's 34, 18, 69, and 87. When kids learn their addition facts that they do memorize, they typically learn the single digits, right? 1 plus 3 and 5 plus 7. They don't typically learn, like 15 plus 62, right? They don't learn 2-digit addition facts that they just memorize and spit out at you. It's single-digit addition. So when you're adding here and you add from, we're going to start in the units column, right over here, 4 plus 8, and you get to 12. Once you hit 12, kids might still be able to do 12 plus 9 because they might have learned up to 12s. I have no idea why up to 12s is sort of the thing, all the rage. I have no idea. But they might not have, right? I mean, they might have just learned single-digit addition. And 12 plus 9 is a much more difficult question than, say, 2 plus 9 would be, right? 2 plus 9 is lots easier than 12 plus 9. So here's what scratch addition does. Scratch addition says that anytime you get to a 2-digit number, you scratch. 4 plus 8 is a 2-digit number. It's 12, so I scratch. And I only remember the units digit. What's the units digit of the number 12? 2. And I do 2 plus 9 instead. So what's 2 plus 9? 11, which is a 2-digit number, so I scratch. What's the units digit of the number 11? 1. And then I add 1 plus 7 together, and I get 8. So what is the net effect of my scratches? The net effect of my scratches is that every time I got a 10, I scratched. So all of those scratches, if I count them up, and I had 2 of them, I carry that number to the next column over. Because I just forgot about them. I ignored them, right? I got a 10 in my wallet, and I stuck it in my savings drawer, right? And I ignored it, and I focused on just the single digits that I still had, the ones that were in my wallet left over. And I can do the same thing. 2 plus 3 is 5. 5 plus 1 is 6. 6 plus 6 is 12, so I scratch and I remember the 2. 2 plus 8 is 10, and so I scratch, and the units digit is a 0. How many scratches did I make? 2, which I would carry over to the next column. There's nothing in the hundreds column right now, so I just end up with a 2 at the end of that value, or at the end of that column. So what you're doing is you're only doing single digit addition with scratch addition. Every time you get a double digit, you scratch and you let that number carry over later. Because I'm telling you what, when you got to here and we said, okay, we had 12, and then I said 12 plus 9, that's 21. The number just gets bigger and bigger, right? And the longer the list of numbers, the bigger and bigger those numbers get when you continue to add to them in the same column. And it becomes more difficult to remember the pieces as you work your way through. All right. So what we're going to do next is that we're going to look at how addition works in other bases. Now, I mentioned back in section 3.1, I mentioned it last time about section 3.1, that part of the idea of working in other bases is to put ourselves in the position of students who are less familiar with base 10 than we are. That's really primarily the goal. And to also better understand why we do the things that we do in base 10. What is this thing called carrying? Well, it's this regrouping business, right? So we're going to take a look at a couple of examples in other bases and think about how we work with addition. So I want you to recall base 8. Base 8 has the digits from 0 to 7, right? The number 8 is represented by a 1 followed by a 0. The tens place is actually the eights place. The hundreds place is the 8 squareds place, or 64's place, and so on. So we're going to take a look at what it looks like to add 3, 4 base 8 to 1, 7 base 8. Okay, so we're going to add just like normal. Okay, I mean, I shouldn't say just like normal, but just like we would with base 10. Okay, we're going to do the standard algorithm first so I can show you what that looks like, and then I'll do another one of the new algorithms that I've shown you, and you can see what that looks like in their base as well, in this base 8. So if I were to add in the standard algorithm, I have 4 plus 7, and I would get 11. Right? Everybody good with that so far? Nothing different. How many 8s is that? 11 is 1 8, and how many 1s? 3, right? So it's 1 8, so we carry a 1 over, and I have 3 1s left over. That's really what happens. If we did this and we got 11, we would say 11 is 1 10 and 1 1 left over. That's why we move the 1 over, is because it's 1 10. So then I have 1 plus 3 plus 1, which is 5. So this is 5, 3 base 8. Let's do this with opposite change. Okay, so opposite change says that I want to kind of make some zeros in places. I'd really like there to not be numbers that aren't 0 involved so much. And I can very nicely do that. If I add the number 1 to 1 7 in base 8, what would I get? I'd get 2 0. Yes, I would. There's that 0 I'd like, right? Because there's no 8s in base 8. I have to carry it on over. Opposite change, though, says if I add a 1 somewhere, I have to subtract a 1. That's fine. What's 3, 4 minus 1? 3, 3, right? That's good. But look what happened. 3, 3 plus 2 zeros, actually really nice to add. What do you get? You get 5, 3. No rethinking of how many 8s do I have and carrying things over and what do I have left. None of that happens. It actually works really nice on that particular problem. Let's try a base 3 problem. 1, 2, 1, 2, base 3, and 1, 1, 2, base 3. All right, so we'll do our standard algorithm again. 1, 2, 1, 2, and 1, 1, 2. All right, units column. 2 plus 2 is 4. How many 3's are in the number 4? 1, 3. So I carry the 1 with 1 left over. So now I'm in the 3's column. It's got a 1, 1, 1. 1, 1, 1 is 3. How many 3's are there in the number 3? 1, which I carry over, and I have 0 left over. 1 plus 2 plus 1 is 4, which is 1, 3 with 1 left over. And then 1 plus 1 is 2. So it's 2, 1, 0, 1, base 3. That's what the standard algorithm really looks like in base 3. I'm going to do lattice for the other one on this one. 1, 2, 1, 2, 1, 1, 2. Okay, so remember what the lattice diagram does is it splits the place values. So the top corner is the 3's, the bottom corner is the 1's. Okay, it's the 3's place and the 1's place because we're working in base 3. I can move from left to right if I wish. This is just the number 1. That's fine. 2 plus 1 is 3, which is 1, 3, and 0 1's. 1 plus 1 is 2. And 2 plus 2 is 4, which is 1, 3, with 1 left over. It's the individual pieces. And then I extend my diagonals, and I have to now work from the bottom right-hand corner. Well, that's a 1. My next diagonal has a 1 plus a 2, which is a 3, which means that I have to carry that number over. 1, 3, and 0 1's. Okay, 0 left over. In my third diagonal, I have a 1 plus a 0, so that's a 1. And then I have a 1 plus a 1, which is a 2. So I end up with 2, 1, 0, 1, base 3. Okay, so here's what I'm going to do. I'm going to keep going. We'll go till the class ends, of course, and then I'll record a secondary video that's the last pieces of whatever I don't get to, and you'll have your group work and your homework assigned as homework, okay? So when you come back on Monday, I'm going to keep this recording on this so that in case you need to re-listen to my instructions, you have that ability. When we come back on Monday, you'll have 3.2 homework, group work due, and you'll have 3.3 homework, group work due. You'll want to watch all the videos that are going to be posted, but the 3.4, I will only post half of that, and we will finish that and do group work in class for that. Is that clear? Okay, let me show you a few things that are left. What's left in this section is mental math. So this is math that we do in our heads, but you have to understand, of course, that I can't see inside your head, right? So you have to show me what you're doing, even though it's stuff that should be able to be done mentally. And then computational estimation. So sometimes people get confused with the difference between mental math and estimation. They're not the same thing. Mental math means something that I do in my head, but I get the exact answer, okay? Estimation means I've changed something so that I can do it in my head, and that's great, but I'm getting an approximation. So please keep those two different terms separated in your mind. They show up at the same spot in the lesson, but they're different. So the first one, mental math. Mental math, first off, we're doing an algorithm that's called adding from left to right. So here's the way that this algorithm works. You start with the first number, 46, and then you add the largest digit that we have, the 3's place value. So in this case, 3 would be 30. 46 plus 30, it's nice to add because I'm only really adding one of the two digits together, right? The 3 and the 4. I don't have to worry about the 6 because it's adding to 0. So what's 46 plus 30? 76. And then you add on the ones piece afterwards, 8. So 76 plus 8 would give me 84. Okay. I totally lied. That's breaking up and bridging. What I just said is called breaking up and bridging. That's the second one here. Hang on. I'm going to cut this and paste it. I got ahead of my notes. Okay. It's just not going to be there. Let me try again. Left to right. Left to right is the same thing as column addition. You add the 30 and the 40 together, so you get 70. You add the 6 and the 8 together, and you get 14. And you add those two together to get 84. Okay? So you're doing, you're isolating the place values, and then you're adding the two values you get together. 30 plus 40 is 70. 6 plus 8 is 14. That's 84. Okay, so that's adding from left to right. Column addition is what it's also called in the other bigger versions that we had. Breaking up and bridging is the one I just inadvertently told you. You start with the whole value of the first piece, 46, but you only add one of the place values, the biggest one, 30. So you have 76. And then you add the remaining one's digit to that, 76 and 8 would be 84. So that's breaking up and bridging. So what you're really doing is you're breaking the 38 up into 30 and 8. Trading off has been a part of this section, or at least this material in this book for a while. But trading off is really just opposite change as well, which we've already encountered. So trading off or opposite change means that what we want to do is we want to make one of those numbers a number at the beginning with a bunch of zeros after it. And that's really the goal of trading off, okay, or opposite change, is to zero things out. So we want to take one of these numbers and make it a 0. And sometimes there's a natural choice, sometimes they're not. There is not. Which one of those numbers would be the nicest to turn something into a 0? 38. What would I need to do to 38 to turn the 8 into a 0? Add 2. So if I add 2 to 38, I get 40, but I have to inflict the opposite change to the other number. So the 46 actually then would be minus 2 and give me 44. The whole point is that it gives you something that adds a 0 or puts a 0 in the ones place, or if it's a bigger digit, maybe in the ones place and the tens place and maybe the hundreds place or whatever. So I end up with 84. And the reason that this trading off opposite change works nicely is because you can do small values, right, 2-digit numbers, with that pretty reasonably, I think, in your head, right? You're compensating, but you're not having to compensate for a whole bunch of digits. Like, I don't think you can do this with a 4-digit number and call that mental math. But I think with a 2-digit number, it's a quite reasonable thing to think is possible. Compatible numbers. Compatible numbers goes back to one of the strategies, the basic addition strategies that we talked about early on, which is the idea of making tens or potentially making hundreds. It's grouping numbers together that are just nice to add together. Do you see any two of these that are just nice to add together?
60.
Yeah, 60 and 40 are nice to add together because what do they add to? 100. Any other numbers that look nice to add together?
70 and 30.
Yeah, 70 and 30 are very nice to add together because, again, they equal 100. So the only one I didn't use in this case was the 50. But I'm telling you what, 100, 50, and 100, that works pretty nicely to give me 250. But if you started from this and just worked from left to right, it's not going to be that quick and easy to deal with. 40 plus 30 is 70, but now I have to add 70 and 50, and after I do that, I have to add another 70 and then another 60. The ordering of that was not particularly nice when it began, so just changing the order up. And we're able to do that because we have a commutative property and associative property that allow that, right? Yeah. Okay, we'll stop with this next example. It'll be our last one, and then I'll do the computational estimation as a video and the rest of its estimation. So the last video that I'm doing will be all about estimation. This one is actually called making compatible numbers. Do you remember the doubles example where I said that if people knew that 3 plus 3 is 6 automatically, then 3 plus 4 they could reach that by looking at the 3 plus 3 fact? It's this kind of like that. 35 and 68 are not compatible numbers, but they nearly are. If I changed one of them just a little bit, they could be compatible. And you can argue which one's nicer to change and which one's easier to change. It doesn't really matter. You can pick your own pick. I think that the 68 is nice to change to 65. 35 and 65 are compatible numbers. And by compatible, what I mean is that they add together to something nice. What do they add together to? 100. Yeah, they add together to 100. But what change did I actually make? I mean, I changed 68 into 65. I got to compensate for that. Yeah, I need to put 3 back on. I eliminated 3 of them in order to make that happen, so I have to add my 3 back on to get 103. So the idea is to alter one of the numbers just slightly to make them compatible, right? And then to compensate for the change that I've made. All right, I will post a video for the estimation part of this, and then 3.2 will be finished.